I've contributed to this work, but also a lot of it, really, and most of it, in fact, has been done by Xin Jiang and Erica Galetti, who were PhD students at the University of Edinburgh. Erica's a postdoc, and Brian Bapty gave us some of the data that we're using. So this is work that was sponsored, in fact, by Schlumberger up the road, with a couple of other companies, and an EU-funded project as well. So the title of the talk sounds simple, but it needs a little bit of discussion first. I mean, there's two words there that we understand very readily individually. So tomography, constructing an image of a slice or a volume of a solid medium. And for me, that's going to be constructing an image of the solid Earth from measurement taken at the surface of the Earth. Nonlinear, anything which is not linear, not a line, not a hyperplane, is nonlinear. But what is nonlinear tomography? That is less clear, certainly ambiguous. So presumably what it means is constructing the image, accounting for the nonlinearity of the physical relations between the image and the data that we get. It means something like that. But we need to be a bit more specific. Here's a nonlinear relationship. If I just think of M here as the model parameters, and D is the data that I might record, so this is a nonlinear relationship between the model parameters and the data, then somehow I want to do tomography. If M here is going to represent my image of the Earth, then I want to, for example, record, not working anymore, record some data and be able to find all of the different images, so parameter values, which are consistent with that data set. And clearly in this case, there are two. This one and this, these two parameter sets, or values in this case, are consistent with that data. So I've got two images. Now, I need to find both of those in general imaging problems, because I'm going to make decisions based on the images. You can imagine in a medical ultrasound scanning experiment, if I have only one of those two images and one of them has an anomaly which could represent something worrying like a tumor and the other one does not, and I find only one of those two and I don't even know the other exists, or whether it does or not, then I will be essentially flipping a coin with that patient's diagnosis. And the same thing happens in the solid Earth when we're making decisions which involve usually a lot of money to do with resource extraction or to do with storing waste like nuclear waste storage or CO2 for climate change mitigation in the subsurface of the Earth, with high risk, high cost operations. And we need to know all of the different solutions to the problem. So a typical way that we solve these problems in the geosciences is to that's why we want to do nonlinear tomography, is to find both. But a typical way that we do solve these usually is to take a prior best estimate of our image or our model of the subsurface and linearize the function or the physics around that model. So linearize it around the gradient of that part of this physical relationship, assuming that this model is close enough that we're going to stick within this region here where the approximation is good. What we'll do is we'll then forget about the original physics, the full physics, and try to solve that problem, or we will solve that problem. So we'll find the model that's consistent with it, it's this one, get a new estimate, and then we might iterate the process. So we'll linearize again, find another best estimate, model M2, and gradually we'll move towards a model which really does fit the data according to the nonlinear physics. We're better than model M1, better than the first model, so we're moving in the right direction. The problem is that this is not really nonlinear tomography, because in no sense have I taken account of the nonlinearity of that function. I've always solved a linear problem at every single iteration. And clearly, carrying on with this is never going to find me my other solution, which may be the true one. That might be the actual structure of the Earth or the body or the non-destructive testing widget that we're testing. So we need to have fully nonlinear tomography in order to solve these. So I would rather term this kind of operation iterated linearized tomography. And in particular then in this talk, what I want to talk, when I say nonlinear tomography, I mean non-linearized tomography. tomography. I don't want to linearize the physics at all, because then I've lost all the information in that nonlinear curve. I've thrown it away. So I'm going to show that by doing this, and in fact what I'm going to do here is I'm going to use Monte Carlo methods to do this, but this is not a talk where I'm trying to sell the particular methods we use. That's just what we used. It's rather, I'm going to show you the advantages if we can use the full physics. What do we get in the images which is significantly better than if we linearize the problem? So I'll show two specific things that we're going to get. And so it's really a pitch, if you like, that we should stop focusing on linearized methods so much and put a lot more effort onto methods that can solve the fully nonlinear problem. So the first one, I'm going to look at seismic tomography, so using seismic data from the surface of the Earth to try to image the Earth. And the main thing that I'll show you in that first example will be that the uncertainties so that we get are trustworthy, and we can actually use them independently of the structure that we see. So we can actually interpret the uncertainties directly in a way that we simply can't when we use linearized methods, and I'll show that. I then want to switch physics. So that's going to be using the wave equation, actually the iconal equation that comes out of it. And I want to switch to electrical tomography where we have a Laplace equation governing the system and show that exactly the same results and topologies that we will see here appear in the electrical case. So the lessons that we learn here will appear to translate to other physics. But in addition, excuse me, in addition, what I want to show is that when we include the full nonlinearity of the problem, we have better imaging, in the sense we have far better penetration into the object and far better resolution. So the nonlinearity is your friend. It shouldn't be avoided. It's got a lot of information in there. And we'll see this specifically that in this example that I'll show here, a very simple example. If I take the standard method, which is used in industry and in academia actually, a standard freeware code, and compare that to the fully nonlinearized code, we get a factor of 8 increase in the depth of the image. So 8 times the penetration into the object. Both of these will be examples in two-dimensional imaging, so slice tomography, and then I'll just show at the end that there's nothing in particular that these lessons, none of these lessons cannot be translated into the 3D case. So first of all, I'll just talk about the data. The data that we use, because I know most of you won't be familiar with geoscientific or seismology. So I'm going to be using ambient seismic noise. So I'm going to study the UK for this example because it is surrounded by ocean and sea. So we have waves hitting the shore of the UK, and constantly that is vibrating the solid Earth. And that solid Earth vibration sends waves which bounce around under the UK crust into the mantle and come back up and go out the other side. And we've got these sources of energy on all sides. We're surrounded by sources of energy. And we're going to use those sources of energy to image the structure, the seismic structure of the UK. Now the way that we do this in seismology is we record that data for very long periods, maybe a year, just these ambient vibrations, at a number of stations which we call seismometers. I'll show you the actual distribution in a moment, but they're distributed across the UK. And if we take very long records of this ambient noise, and we can have an application of Green's theorem, which says that if we simply cross-correlate those records in pairs, then the cross-correlation is itself a signal that it has very similar properties to a seismogram, the kind of thing that you've seen before. When earthquakes occur on the news, you see these things. But it's a seismogram that, as though it was recorded at one of the stations, and as though a source, an impulsive source of energy, had occurred at the other. So no source actually occurred there, so we call it a virtual or imagined source. But we get a seismogram as though it did occur, and it was recorded here. And so this is called seismic interferometry. There's a whole field associated with that, but that will give us seismograms as though waves propagated from there to there. And we will use those to find the travel times of those waves. And we'll do that between every pair of stations, so that we'll turn each station into a virtual source recorded at every other station. In other words, we get travel times between the whole network of stations. And that's what we want to now solve tomographically for the seismic wave speed. I'll call it the velocity structure, the wave speed across the UK, but localized to every point. So I want a map of the velocity structure across the UK. So I take these cross correlations, I find the interstation travel times, and they will be my data. I want to solve for the velocity model, and I may well use model in a non-mathematical way here. I'll try not to, but I probably will. In geophysics, a model is a model of the Earth. So it's, in mathematics, a model is a relationship. So the parameters of the relationships are what we call a model. Now, I'll try to say parameters, but if I say model, that's because I'm talking geophysics by mistake. So we're going to solve for this velocity model, in other words, the parameters of our relationship between the data and the wave speeds that we want. It's solving a typical problem like this, where the data are the travel times, the velocities are what we're looking for, and G is significantly nonlinear, and I'll show you that in a moment. So this is the distribution of stations. It's highly irregular. There are many different ages, if you like, of these various networks. But what we're going to do is we're going to use every pair of these to get a travel time between them, and that's the data set that we have. I'm going to use Markov chain. It's a reversible jump one, and essentially I'm going to use it to get me samples of the Bayesian posterior distribution. So just for anyone who's unfamiliar, I'm sure most are, what we're actually asking here is that for any particular velocity structure of the Earth, what is the probability that it is true given the observed travel time data? Now that is all I can ask of my inverse problem. That is the solution to the imaging problem. I'm always going to have a variety of different parameters that fit the data, and I want to know their relative probabilities. Bayes' theorem says that, okay, there are three terms that this depends on. The likelihood, which is, well, okay, if that particular model was true, what's the likelihood that I would have observed the data? If this model is inconsistent with the data, this is going to be very low, and then so should that be. So this makes sense. The prior distribution doesn't depend on the data. It's just what we knew independently of the data set that we recorded. And the evidence is this term down the bottom, which doesn't depend on the model. And actually, this is the probability that we could have observed that data given all of our assumptions about the model data relationship and our prior. So basically integrating over all of that space, how likely is it that we could have observed that data? But this is the answer we want, and this is how Bayes' theorem says we can get it. The problem is that we have to evaluate this for a specific set, a velocity model, a specific map or image. So which image do we choose to evaluate the probability of? There are many. And so what the Markov chain does is it tells us which sequence or chain of images we should calculate their probability, for which we should calculate the probability. And the nice thing is that it will generate samples of this probability distribution. Now, I'll show you how this works in the algorithm that we use. So this is what we call a geophysical model. It's a velocity model, so it's a map. In the background there you can see the UK, and this is a completely random map of velocities. You can see it's tessellated. There's a random number of cells there. They're Voronoi cells. There's a random number. They're randomly positioned, random shapes, sizes. These colors represent the seismic velocities in each, or the speeds, if you like, in each cell. So red is slow, blue is fast, and they are randomly assigned. So it's a completely random map of seismic velocities. And the Markov chain is generated by an algorithm that says, okay, well, to start with, let's see how consistent this model is with the data, so the measured travel times. So the first thing I have to do is calculate the travel times between the stations, which you won't be able to see, but there are little white dots here. So the first thing I have to work out is what path would the seismic waves take between those stations. So that's the ray, it's the fastest path. And we can calculate those paths, and they're up here now. You may not be able to see them from the back. What we then do is we then perturb the model. We might perturb it, the velocities. We might move the cells, we might kill off a cell, so change the model dimension, or we might add a new one, randomly increasing the dimension of the parameter space. So in this case, let's just say we take one of the cells and we just change its velocity from fast to slow. We recalculate the data for this new model, and what you can see is, remember, this was just a single cell change in velocity. For those at the front, they'll see that actually the ray structure has changed very significantly all over the model. So out in the North Sea here, for example, we now have a different geometry of rays. So there's nothing, even though we make a local change, there's nothing local about the change in the data. The rays flip. And that means that under this new model, we would interpret the travel times of those rays as telling us about information somewhere completely differently. So if you like, we're going to do this many, many times, and what this really means in a mathematical sense is the metric by which we are evaluating the consistency of that model with the data changes for every single model. The metric changes. We're not using the same metric for any two models. So, the next thing the Monte Carlo algorithm does is calculate an acceptance ratio, which I'll come to in a minute, but it basically is a probability of rejecting this new model, in which case we just delete it and go back and propose a new one, or we would accept it, it becomes our new model, and we move on. And we're going to do this millions of times, in fact, and the nice thing about this algorithm, is, or the key to it, is that acceptance ratio. It looks like this. It's basically the ratio of the priors of the new and the old model, the likelihoods, the chance of moving from the old model to the new and back again from the new to the old. If that was asymmetric, we'd have to account for that. The Jacobians take account of changes in dimensionality. But the nice thing about this thing, which isn't this object, if you like, which isn't obvious here, is that firstly, the samples are naturally parsimonious. This algorithm will not just keep adding model parameters ad infinitum to better fit the data. It prefers simpler models which fit the data to within their uncertainties. And it also ensures the samples are distributed according to the posterior. So we get more dense sampling where there is a higher likelihood of those models being true. So we can evaluate the posterior from their density of the samples. I should also point out it is hierarchical based because that sigma there is the uncertainty on the data, which we don't know. Typically, we don't know that in seismology, so there's an applied uncertainty there with a parameter or a couple of parameters which govern those. Now, the problem that we have then is we're going to get a lot of samples that look like this, and they don't look like maps of the Earth, right? The Earth geologically doesn't look like that. And we're going to get thousands or millions of these. So what we do is we remember that in fact it's the family of all of them that represents the solution. It's not any one of them. It's all of them that is spanning the space of possible velocities. So what we do is we put a regular grid over the top, and we're just going to use these as points at which we want to construct an image. So we're just going to examine each point in turn, so just keep your eye on one, say that one there, and then we just look through all the different velocities that occur at that point in all the samples, and then we can just calculate statistics of the velocity. For example, we could calculate the mean. There's the average model, and you see now the average model is smooth. Or we could calculate the variance around the mean, and there's the standard deviation of that. And so we get an uncertainty map across these models. Now these are just two statistics, and I should say these statistics, the mean and the standard deviation, are not models. They're not actually achievable in the Monte Carlo. They are statistics of the distribution of the family of all the models. Nevertheless, when we look at them, so for example at the average map, we see structure that we should see. We see the basins as low velocities, the Midland Valley Basin, the Irish Sea, the London basins. These are deep sediments where we should see slow, relatively slow velocities. We see the high velocities of the basement rocks of the Scottish Highlands, of the southern uplands, the Pennines and the granites of Wales and Cornwall. So we see structure that we should see, which is good. But the interesting thing comes when we look at the other map, the standard deviation, because this contains features that we've never seen before. And they are these loop topologies that you can see, for example, here. Now clearly, they are something to do with the anomalies. That's quite clear. But what on earth are they? As I say, they've never appeared before on a tomographic uncertainty map. When you look at them, they become concerning because they contain the highest uncertainties on the entire map. And what's more, when you get your eye in, they're everywhere. Okay? They surround all of our anomalies. So what's going on? Well, the first thing is, I mean, these haven't appeared before, so, and we didn't know what they were. So the first thing we said, well, okay, is it to do with the higher order physics? We haven't linearized. So let's do the same thing with the same data set using iterated linearized, and then have linearized uncertainty estimates, and that's what you get, and they're gone. So clearly, these loops are to do with second or higher order physics. And by throwing out that physics, we simply don't see the loops, which is why they've not been seen before. If we want to understand a bit more than that, we have to look in a bit more detail at the loop. So let's just have a look at that one. And we'll look at 3 points. So the yellow point is right in the middle of the velocity anomaly. Okay? And if we just look, remember at each point on the map, we have thousands of different samples of the velocities. So let's just look at that histogram of the posterior distribution of velocity at that point. And this is it. And what we see is it's definitely upper bounded by about 2.5-ish kilometers per second, but there appears to be no lower bound. I mean, the lower bound here is simply imposed by our prior. We just stopped sampling at some point. So it's basically unbounded on the lower side. If we look at the magenta point over there, we see the same thing. We see that same peak, but there's a second mode to the distribution, which is a high velocity. And similarly for the green point, we see exactly the same thing, an unbounded lower velocity, but a secondary peak. So, to understand that, we just look a little bit more at the physics of the problem and why this is nonlinear at all. What is the nonlinearity that gets kicked out when we linearize? So let's take the simplest possible tomography problem. It's got one anomaly, that black circle, so that's a low velocity anomaly in a high velocity white region. And let's say we've got one source and one receiver, so one travel time that we measure, t1. So we're going to try to just think about the tomography problem with a single travel time. Now what's happening is the fastest path between these two goes around the edge, it refracts around the edge of the anomaly, so it's traveling in the white medium. It's traveling quickly. So it's quicker to go around the edge than through the middle, because the middle is slow. Now I can increase the velocity of that anomaly, and it'll still go around the edge. It's still experiencing the same white velocity, so it's got the same travel time. These two both perfectly fit the data, and so does that one. But now I've reached a point where it is equally fast to go around the edge or to go through the middle. So both of those waves will arrive at the same time, and I will still get travel time t1. But if I just go even a tiny bit further, that path around the edge is now slower because it's quicker to go through the middle. But at this point, the ray path has flipped from one side to going through the middle, and my travel time changes. So this ray path flip is exactly the nonlinearity that disappears when you linearize. When you linearize in seismology, you fix your ray paths. That's how you linearize the problem. And you need ray path flipping, moving, in order to see what's going on or what's about to come. I'll show you why. I can change the size of the anomaly. So this one here would be faster but larger. It would give me t1. I could make it smaller and slower, and it would still give me the same travel time until I go past the threshold when the ray path flips from a straight line to going around the edge. And then I get a different travel time. And of course, I don't need to do either of these. I can change the shape of the anomaly. And the ray path will simply avoid it. It'll change its shape to avoid the anomaly. And obviously, at some point, I could change the shape such that it can't avoid it, and I would change the travel time again. So what we see is that all of those models fit the data exactly. So they represent the non-uniqueness in the solution. And how does that relate to what we've just seen in the seismology? Well, there's our anomaly. That's the uncertainty loop around the outside. Well, the yellow point, remember, that was in the middle of the anomaly, so it's a bit like this yellow point here. And what we can see, we discussed moving from this model to that one, but actually, if we just go back in that direction, clearly I can make that as slow as I like, and the ray path isn't even sampling it. So there is no lower bound on the velocity, which is exactly what we saw at the yellow point. Physically, it makes complete sense. The green and magenta points are on the boundary of the anomaly. So they're a bit like points there. Okay, that's the same point just shown. And what we can see from these points is that if they're on the boundary, or close to the boundary, is that sometimes they're outside, here, here, and here. And sometimes that same point is inside there, there, and there. When it's outside, it's got a high velocity. When it's inside, it's got a low velocity. And when it's inside, we know that velocity can get as low as we like. So it's either outside or it's inside. Therefore, we've got two peaks, and it's relatively unlikely that it's going to be in the middle. Okay? So these loops, what they're telling you about is our uncertainty in where the boundary of that anomaly is. Is that point inside, in which case the boundary is here, or is it outside, in which case the boundary is there? And we don't know. So the width of the loop tells us the uncertainty in the geometry of the structure. And if you're still not convinced that that's the reason, well, let's say these represented, or in some sense representative of the type of non-uniqueness, well, I could just treat them just in the same way as my Monte Carlo samples, and I could point by point take the average and the standard deviation and make a map of the standard deviation. And if I do that, this is what I get. I get very low uncertainties everywhere except where it's red, and I already see my loop emerging. So the uncertainty loop is emerging from this type of physics. And this is why you don't see uncertainty loops when you linearize problems. Which is important because they're the highest uncertainties on the map, they are everywhere, and indeed the largest loop is this one right around the edge, which has exactly the same meaning. What that's telling us is we don't know where the edge of the UK continental shelf is from this data set. It could be a way out there, it could be tightly defined, but we don't know because we haven't got any data to define it. So it is telling us the width of our uncertainty in the geometry. So what we saw there is that these loops are themselves interpretable. I mean, they are telling us about the geometry of our anomalies. They're not telling us the value of the velocity in the anomaly, but they tell us about the geometry of the model, of the subsurface structure, I should say. It occurs, or we see that those high uncertainties because what's happening is as the anomaly changes shape, the physics allows the waves to just change shape with the anomaly. The anomaly just pushes the ray path around so that it avoids the slow and goes through the fast part. Now, there's lots of other physics that has a similar kind of property. So at this point, when we published that stuff, we postulated or conjectured that actually these loops must exist in most nonlinear tomography problems. We've just never seen them because we linearize. So we tried a separate type of physics, electrical tomography. This is now just a schematic example I'll go through very quickly just to show you the same kind of effects and then a few more. This is now a cross-section through the Earth, and this is representing the electrical resistivity, so how resistive the structure is to electric current. And we've got some anomaly there. So the way that we get information about this resistivity structure is we inject some current, literally put two pegs into the ground, metal pegs, and we put a battery across them, inject current, which creates a potential field in the subsurface. And immediately you can see that the anomaly is perturbing the physics. It's pushing those field lines away. Now, how do we get information, so data, to try to reconstruct this resistivity structure? Well, we just put another pair of pegs in with a voltmeter, and the potential difference between the two is measured on the voltmeter, and that's our data. Okay? And that's it. Very simple experiment. It literally requires a voltmeter and a battery. We don't just do it in one place. We could change the scale, in which case we tend to see deeper if it's more spread out, and as it becomes tighter together, we see shallower, so we can see different depth ranges. And we can move, obviously, along the surface of the Earth to get information laterally. In reality, we've just put down a row of these electrodes, and we just switch them between sources and receivers, if you like, in various different combinations until we've gone through the lot. So that's our data set, and we want to solve for the resistivity structure. Now, we're going to use exactly the same algorithm. I won't do it again. We're going through solving for Bayes posterior, and I'm just going to show you the final results. So we got, I think in this case, about 500,000 samples, and I'm just going to show you the means and the standard deviation maps, because you're used to those. We're going to do it for just a synthetic model that is about the simplest, interesting one that we could think of, which has low resistivities and a high resistivity, something like a dike, so a volcanic intrusion or igneous intrusion into the sediments around, and that's a very common structure that you see in the Earth. It's only 30 meters deep. This is a shallow surveying method. Here is, if we just put in those electrodes along the surface and we use the Monte Carlo algorithm with nonlinearity to image, this is what we get. okay? And there's the standard deviation, and there's the true model. So we're doing a good job down to a depth of around about 12 meters. So we're seeing pretty much the correct structure. And at 12 meters, that's where, as we should hope, where we get it wrong, the uncertainty increases very significantly. So the whole thing is consistent, and we're seeing structure to about 12 meters in the average or the mean structure. But in addition, if we just focus on the uncertainties, we see this kind of odd structure here. And this is, again, one of these loops. It's actually truncated by the model boundary in this case, because we haven't solved for anything up here. But it is two very high uncertainty regions here, which link up down here. And this area here is much higher uncertainty than outside. So there is half a loop there. We know it's the same because if we look at a point on the inside and look at its posterior histogram, it's very sharply peaked at one value. And if we look at a point on the boundary, it's got two peaks. So it's exactly the same physics. It's the uncertainty and where the boundary is. That point is either inside or outside of that anomaly, and we don't know which. It's just exactly the same as these loops that we saw here, the same cause, just a different physics. So that shows that really these things do seem to translate, these topologies. Now, the other interesting thing about this is, okay, in this case, the average map sought about 12 meters, but that's not the only statistic we could calculate. So we could, for example, take the histograms at every point and calculate the median value, or the maximum posteriori value of those histograms. And now you see that we get very different depth resolutions depending on what statistic we use to examine the image, or the set of images. In the posterior case, we're really seeing down to about 28 meters, something like that. Now, if we want to compare that with what we would normally get, if we just use the standard methods, so linearized methods, this is the linearized method. And this is an automatic method which is used as standard across the electrical surface resistivity domain, if you like. It sees to about 3 meters depth with the same data set. So literally, that one is at least 8 times the depth that it's seeing. And even if we use this, so that's with the maximum posteriori, and in addition, of course, because this is linearized, you don't see the uncertainty in the structure. You just see these uncertainties here, which are actually not correct. Of course, we should be clear here, that took 500,000 iterations, and that took about 100. So that's why this is, if you like, a high-performance computing application, for this type of workshop. But there's the main, that's the main difference. So I suppose the main thing I wanted to get across here was that the nonlinearity is clearly not something to be avoided. It might seem simpler to just linearize and use standard methods and do some research on those, but actually, Monte Carlo is very expensive. If we could find some cheaper methods that don't involve sampling to solve fully nonlinear problems, then the advantage we would get is really very significant, just by including the full nonlinearity of the physics. And just very quickly show you that this applied to some real data. This is Aberlady. It's one of the key Saxon, it's not a burial site. It's, in fact, archaeologists don't quite know what it is, but it's some sort of site. Somebody's done a map view, sort of just taking the ground resistivity here. You can see some sorts of foundations. So we did a few profiles of just collecting resistivity data. I'll just show you these two, which are quite close together. One is longer than the other, so should see deeper. If we look at the first one, I'll just immediately just go straight to 3 different measures of the actual map, and you can see that down to about 10 meters, we seem to be seeing reasonably consistent structure depending on the measures. These are 2 measures of uncertainty. If we solve with the same data set using linearized methods, that's what you see. And again, we see the same things as before. So if I just go back, we see these loop-type structures and the uncertainty surrounding the anomalies, and we see far greater depth of structure using the nonlinearity compared to the linearized methods. And if we just take the second line, again, very similar structure, and again, We're just not seeing anything like the depth of penetration using linearized physics. I'll very quickly show you an example in 3D because this is just a simple extension. It's the same thing, but now with 3D Voronoi cells instead of 2D. So the same algorithm applies. We just perturb the models. We iterate many times, and we will get a sample of the 3D posterior. And this is really where we want to go. We need to go, actually, to 3D models, particularly for the Earth, but also for non-destructive testing algorithms. And we've just seen medical imaging talk. We need to be imaging 3D structures, not 2D. Here's a very simple synthetic case with 4 layers and a sphere in the middle. I'm just going to take a slice vertically and horizontally and put them up. You can see the receivers we've got here, and we're going to just get travel times between them and invert for now a 3D structure directly. All the different Markov chains take some time. I didn't go into this before. They take some time to converge, actually about 1.5 million samples before they settle down away from their initial random positions. So we basically start taking samples after that, every 100th or 200th sample after that. And that's what you're going to see next. And this is just a set of models. The graphics aren't great. Better if we just look in the 2 planes, horizontal and vertical. And you can see the 4-layer structure emerging with the anomaly varying in shape and magnitude. And if we just again take means, for example, and the uncertainties, we can see that loop structure emerging around that anomaly, and in the vertical direction, again, we see that loop there emerging. Now, so that clearly now is not just a 2D loop, this is now a shell. It is a shell topology for the uncertainty structure. And it's the largest uncertainty on the map, other than this one, which is at the layer boundary between these 2 anomalies, and that is itself a loop. There is a loop truncated again at the edges of the model, which is giving us the uncertainty on the edges of that layer. So these loops, again, just because they're truncated, they're still loops. They are still dominating the uncertainties. So to summarize then, the advantage, if we can get away from linearization, is we use the full physics, which will help us. It will help us if we can. It increases the information that we get about our imaging. These loop topologies are genuinely from the nonlinearity. They dominate the uncertainties, but they're useful because I can interpret that without even seeing the map of the actual anomalies. That's giving me the geometry of my anomalies directly. They encircle the anomalies, and so these are basically Bayesian fully nonlinear uncertainties in the 3D geometries of the solution. So there's my final message. Keep on nonlinearity if you can. Thank you.
There is a short coffee break, and I think we should ask questions during the break because otherwise, very short. Thank you.